Hello everyone. So today we will talk about the mathematical aspect of LC circuit. So in the last class we talked about the LC circuit functioning and working in great detail. So in today's class we will rather try to understand how exactly the governing equation of an LC circuit look like and whether do we get oscillatory kind of an equation. All right. So in physics, we all know that any governing equation is in general a differential equation. So let us try to frame a differential equation for the LC circuit. So let us first draw this LC circuit. We know we have got a capacitor here, which is positively charged initially with this plate, and this plate is negatively charged. And there is an inductor which is connected to this end, and there is no other component being connected. So initially when time t equal to 0, the capacitor is just fully charged, and after time t equal to 0, the capacitor starts discharging through this inductor, and initially a current flows in this particular direction. However, this current will reverse its direction as soon as the charges in the capacitor are completely drained up. In that case, the inductor will generate a back EMF, and that back EMF for some amount of time flow the current in the same direction. But in that particular case, the capacitor will be fully charged once again, and the current will reverse its direction in the next phase. So this continues. That means there is a direct conversion between the electrical energy and the magnetic energy. Magnetic energy is being stored in the inductor, and the electrical energy is being stored in the capacitor. So till that we have understood this physical mechanism already we know. Now let us try to understand the mathematical aspect of it. So how can we deal up with the mathematical part? So we know whenever the capacitor is fully charged, the voltage across it is Q upon C, correct? And once we have got some amount of potential difference across this inductor, as the current will flow, then only we will get this. If there is no current through the inductor, we will not get any potential difference across the inductor. So if there is a current through the inductor, in that case we have minus L di upon dt. That's what is the potential difference across the inductor, and that's to be equal to 0. Why? Because Kirchhoff's law says you must equate the individual potential drops across all its element to the final potential difference which is applied across the circuit. Now in this case we do not have any potential difference applied across the circuit. It is only a capacitor and an inductor which are being connected. So that is why on the right hand side we have got 0. Now since this is I and we have got a Q over here, so what we are going to do, we are going to convert the current in terms of the charge, and we know current is equal to rate of change of charge, but in this case we shall construct current to be minus dq dt. Okay, because once the current flows, the charge on the capacitor plate decreases. So that is the reason why we get finally, suppose this is equation number 1, from there we get Q upon C, then minus minus plus L d2q upon dt2 to be equal to 0. Alright. So if we do some manipulation, let us write this particular term uh, in the beginning, plus Q upon C, that's to be equal to 0. So we are going to get d2q upon dt2 plus 1 upon LC. Let us write it like this, whole into Q to be equal to 0. So this is actually the governing equation. Alright, this is the equation which governs the oscillations in LC circuit. So I can also write it to be the governing equation. Alright. Now look very carefully how exactly the form or how exactly this equation look like. This equation is uh, this equation pretty well matches with the equation of simple harmonic motion. I mean, let me change the slide and write it somewhere in the next slide. So let me first write this equation, d2q upon dt2 plus 1 upon LC whole into Q to be equal to 0. This is what is our governing equation. Now this equation matches up with the equation of simple harmonic motion. How exactly? What is the equation of simple harmonic motion? That was something like this: d2y upon dt2 plus omega square y, that's to be equal to 0. Now if you compare the terms, in place of y here we have got q in LC circuit, in place of t we have got t, there is no issue regarding time, and in place of omega square we have 1 upon LC. Now that implies what? That omega equal to 1 upon square root of LC. And we know that this is being the resonant frequency. So whenever we have got the L and C connected across it, the circuit oscillates at its natural frequency omega naught, and that omega naught is given by 1 upon square root of LC. So this equation has got a direct link or very much equal or in a sense similar in nature to the differential equation of simple harmonic motion. So both these equations, I mean, since this equation is something where a bob of a simple pendulum or a mass connected to a spring oscillates and it gives you a simple harmonic motion, similarly here you will get a simple harmonic motion for the charges and the current. Got it? So since this is a differential equation of charge, so you are going to get the solution of this differential equation in terms of charge only. And that solution will be written as q is equal to some q max, which is the amplitude of the charge. So cosine of omega naught t plus phi. What is omega naught? That is what is the natural frequency at which this circuit actually oscillates. All right. Now, question is, we do not know here phi. What is the value of phi? That is something we do not know. Qm, we can understand that this is the amplitude of the charge, because charge varies. In fact, in the yesterday's class, we have talked about at what time, for example, if you have got the, if you have the charges to be maximum, say for example, at whenever the time t equal to 0, in that case charge will fall off like this, and this is time t equal to 0 because charge was maximum in the capacitor, and as time increases the charge oscillates sinusoidally, and current was initially 0 and current will oscillate in some different fashion. So let us not concentrate on to that, but one thing is sure, that charges will oscillate simple harmonically. But what is this phi? Now for that we have to incorporate the boundary condition. So what is the boundary condition? So boundary condition says at time t equal to 0, the charge q is equal to qm, because charges of the capacitor are the maximum. So that is why if you put this into this particular equation, let's consider this equation to be 3. In that case 3 implies, put time t equal to 0, q equal to qm. So here also we have got qm cosine of omega naught t, because t is equal to 0, so this term vanishes, you only remain with a phi. So this implies cos of phi to be equal to 1, because this qm gets cancelled, which implies phi equal to cos inverse of 1, and cos inverse of 1 means we have got 0. All right, because when this will be 1, cos 0 is equal to 1, that is something we know. So when the phi's value is equal to 0, in that case the cos of 0 will be equal to 1. So that is why the value of phi must be equal to 0. So what is actually the equation 3 look like? The equation 3 in this case, for the case of an LC oscillator, should look like q is equal to qm cosine of just omega naught t. There should not be any phase constant. Okay. All right. So this is what is the governing equation for the charges. Now what about the current? Because already we know that current is equal to minus of dq upon dt. That's what we have considered. With the time the charges will decay, and that is why current becomes minus dq dt. So it becomes minus of ddt of qm cosine omega naught t. So minus qm. Now what is ddt of cos? Ddt of cos is sine, but that too with a negative sign. sine of omega naught t. So basically what we get, this negative sign cancels out, we remain with qm. There will be omega naught coming out, because once again you have to take a derivative with time of this particular quantity. So from there we will get an omega naught. So qm omega naught sine of omega naught t, and naturally this becomes the maximum value of the current. So I can write I max sine of omega naught t. All right. So this is all about the mathematical background of LC oscillator. Now there is one more aspect of this, because in yesterday's class, if you remember, I talked that whenever we have got LC oscillation, actually this oscillation is the oscillation between the electrostatic energy and the magnetic energy. The electrostatic energy gets continuously converted into magnetic energy and vice versa. How exactly the picture look like? At time t equal to 0, whenever the capacitor was fully charged, there was full of electrical energy, say UE, and there was no magnetic energy stored in the inductor. That means UB is, say, for example, equal to 0. This is something at t equal to 0. But as you go on increasing the time, the capacitor discharges through the inductor, current increases. So at different time steps, there are various values of this UB and UE. So let us try to concentrate a little bit on that, and with that we shall end today's class. So at time t equal to 0, whatever energy is there, it is all electrical in nature. So we know that electrical energy stored in a capacitor is generally given by half of CV square, the voltage square. C is the capacitance. But we also know that charge equal to CV, or V is equal to charge upon C. So what we can do here, we can write Q square by C square. So if you just take it, in that case you are going to get half of Q square upon C. Okay, but in this case we shall not write it to be Q, because Q varies sinusoidally. At time t equal to 0, Q happens to be equal to Qm, since, let us write it, since at time t equal to 0, Q is equal to Q maximum, because capacitor was charged to maximum charges. So the charge, or the total electrical energy stored, is given by half of Qm square upon C. So this is what is the energy stored in the whole system at time t equal to 0. So when you increase the time, current flows through the circuit and the capacitor discharges. Where from this energy will convert to magnetic energy? Definitely from electrical, because there is no other source of energy. You are not providing any external source of energy, so definitely this energy is responsible for the decay. So that is why we shall get this energy to decrease. This is the maximum value of the electrical energy stored. All right. So whenever the current flows, some amount of this energy, some part of this electrical energy gets stored as the magnetic energy into the inductor. And we know that magnetic energy stored in the inductor whenever current flows is generally given by UB to be is equal to half of L I square. Okay, but when this energy will be maximum, this energy will be maximum when current will be maximum, and this generally happens when the capacitor is completely discharged at time t is equal to t by 4. So at time t is equal to t by 4, you do not have any electrical energy. UE falls off to 0, because the capacitor is fully discharged. It cannot store any charge, and hence electrical energy stored by the capacitor is also 0. Whatever energy now you have is all magnetic, and you can write it to be UB equal to half of L Im square, where Im is the maximum value of the current, which is given by Qm into omega, or Qm into omega naught. All right, and this particular thing will continue. That means this is the maximum value of the magnetic energy, this is the maximum value of the electrical energy, and whenever you have got intermediate states, then you have got some portion getting converted from electrical to magnetic, or magnetic to electric. I mean, this conversion will continue over the time, and this will repeat itself cycle after cycle. and that's how we get the oscillation. All right. So how exactly we can say that there is a comparison between the mechanical oscillator and electrical oscillator, because LC circuit is an electrical oscillator. So can we draw some analogies? The answer is yes. So what is the analogy? Say for example, if we make some analogical aspect, this is a mechanical oscillator and electrical oscillator. In mechanical oscillator, you have got something called mass, which actually oscillates. In electrical oscillator, you have got the inductance, which is actually responsible for the oscillation. Okay, and in fact, we have already told that uh, the coefficient of self-inductance, whenever we were talking about that, we already told about the physical significance of inductance, that it is similar to the inertia in mechanical oscillators or in mechanics. Why? Because it gives you sort of inertia in the flow of current. Wherever the current should have risen instantaneously, it gives it a slow rise. Wherever the current should have fallen instantaneously, it gives it a slow fall. So that is why the mass has got an equivalence electrical component to be the inductance. Then second, force constant, which is equal to K. In mechanical oscillator, in electrical sense, you have got the reciprocal of the capacitance. That is 1 upon C. All right. The displacement, which is Y in mechanical oscillator, with the equation I have written, many people like to take it to be X or Z, whatever. In this case, we have got charge. Because displacement you otherwise write to be Y is equal to A sine of omega t in mechanical oscillator. In electrical oscillator, we write Q is equal to Qm sine of omega t or cos of omega t, whatever you write. So displacement has got an equivalence with the charge. Then the velocity, which is nothing but displacement over time of the particle which is oscillating. In this case, you have got, sorry, it should have been 3, this should have been 4. In this case, you have got the current, the electrical current, which is I to be equal to dq dt. Forgetting about whether there is plus or minus sign, we just are concerned about the magnitude of it. Then in the fifth position, you have got the total mechanical energy E, which happens to be the sum total of kinetic energy plus the sum total of the potential energy and the kinetic energy. And in this case, you have got the total energy E to be is equal to sum total of the electrical energy, which is given by half of Q square upon C plus half of Li square. Remember, whenever I talk about the sum total of the electrical and the the magnetic energy, I have not written here Qm, or I have not written Im over here, because whenever you have got the I to be Im, that means magnetic energy is maximum, electrical energy will go down to 0. And whenever you have got electrical energy to be maximum, magnetic energy will go down to 0. So that is why whenever we write the sum, that means we write or we intend to show that both electrical and magnetic contributions are present, then we mean automatically that the charges are not at its maximum or the current is not at its maximum. We have got some kind of an intermediate values. There are some amount of charges and there are some amount of current too. So that we have got both the contribution of electrical and the magnetic. So that is why I have not written QM or IM over here. All right. So this is a brief analogy between the mechanical oscillator and electrical oscillator. Okay. So I hope this part is clear in your mind. Please go through your text very carefully, and in a great detail in your textbook this has been explained. So I hope you will be able to understand, and this video will definitely aid in your understanding. Okay. Thank you so much.